Hello fellow problem solvers. So today we're going to be doing a problem from the 2012 Romania Junior Balkan Math Olympiad team selection test, day 3, problem 4. I suggest you try this problem out for a minimum of 40 minutes, ideally an hour and a half to 2 hours, but not more than 3.5 hours. If, on the other hand, you'd like to go along with us, I suggest you try this problem out for a minimum of 10-20 minutes, play around with it, and see what ideas you come up with. And now, without further ado, let's begin. So, this is what the problem is really asking us. It says we have a set A, 1 through 2n minus 1. We're going to remove a couple of numbers from it, at least n minus 1 numbers from it. And if numbers a and b are removed, then and if a plus b is also in a, then a plus b is also removed. And if a is removed and 2 times a is also in a, then we have that 2a is also removed. And we must figure out which numbers need to be removed such that the sum of a minus all those removed numbers is the maximum. Now with these types of problems, there's a general principle which is to play around. Like, if you want to sort of understand what will be the solution and you don't have a good beginning, then the best thing you can really do in the start is play around with the problem. So here, let's say for n equals 2, what do we have? We have the sets 1, 2, 3, and we must remove one number. So here we would, if we remove 1, then we have to remove 2 and 3, no good. If we remove 2, we can just remove 2. And then we'll have the sum be equal to 1 plus 3, which is going to be 4. And that's the biggest sum. So now if we have 3 elements, if we have 1, 2, 3, 4, 5. And here I suggest you take about 10 to 20 minutes and try to play around with n equals 3, 4, 5. And see if you can notice something from these playing around. So for me, for n equals 3, if I remove 2 and 4, I get the sum 9. Otherwise, I have to remove 2 smaller numbers. I can't remove a 1. If I can't do 2 and 3, then I would get a 5 removed as well. If I'm removing 2, I'm also removing a 4, so I have to remove a 3, but then I have to remove another number, so this is the smallest one. I have 9 for n equals 4. I'm removing 3 numbers, and here already my intuition is sort of building up. Again, if I remove 2, 4, 6, I have the sum that's left is 1, there's a 7 here as well. If I remove 2, 4, 6, then I have 1 plus 3 plus 5 plus 7, which is 16. And there's no better way for me to do this. And now I immediately see what I believe to be the solution. I believe the solution is n squared, and we get it when we remove 2 and all the even numbers. And how many even numbers we have? We have 2, 4, all the way till 2n minus 2, which is 2 times 1, 2 times 2, 2 times n minus 1. This is n minus 1 numbers, and we have a sum of n squared. Now this was my intuition, and now I invite you to take another 20 minutes and figure out what would you do next. How would you potentially prove this? Here's what my next step was. So the first idea I came up with was, well, let me try to prove this via induction. It seems to be the most plausible thing. Like, it seems like there's some maybe casework that needs to be done, but let's try it out. So assuming that I know for 2n minus 4, and that the solution is 2, 4, all the way till 2n minus 2, we can also look at this as such that the sum of b is the smallest possible. Instead of a minus b being the biggest possible, then the other one is, say, b is the smallest possible. And I have 2, 4, if I remove these numbers out of the smallest possible sum. Now for n plus 1, I'm removing n numbers out of this set. And now, if I remove a 2, then I can probably have an argument. If I remove a 2, I have a sum that's very small, and I have all my n numbers, I have n numbers removed, 2 through 2n, all the even numbers. If I remove a 1, I just remove all the numbers, and then my sum is huge. So I can assume I'm starting from 3, or at least 3, like it can be bigger than 3. I can start somewhere in the middle, perhaps. And now I was looking at, okay, what if, say, when can I apply the inductive hypothesis? Well, if only one of these two numbers is removed, if say 2n is removed, and 2n plus 1 isn't, I can apply the inductive hypothesis on the rest of the sets, and I'm done. Also, if just 2n plus 1 is removed, I can also apply the inductive hypothesis. If neither one of them is removed, then I have to be a bit more creative. And the way I did this was I realized, let me try to get to n. So I did 1, 2n minus 1, 2, 2n minus 2, all the way till n minus 1, n plus 1, and n gives us 2n. So if I remove n, I'm removing 2n. Here I have, if I remove any two of numbers in these n minus 1 pairs, I'm automatically removing 2n because it's the sum. So this means if I'm not removing 2n, then I'm not removing n, then I'm only removing one number from each of these pairs. And because I have n minus 1 pairs here, that means I have to remove 2n plus 1. And similarly, I can make it this 1 and say, I think I can also get a similar sort of thing for 2n plus 1. And now here is where I ran into an issue. And the issue was, what if both of these are removed? Sort of intuitively, when I played around with like numbers 1 through 9, I couldn't, like I was using arguments that weren't generalizable. I was using the fact that this is a couple of, like if I add 6 and a 5, it's bigger than 9. If I add 3, 4, 5, I get a number bigger than 9. I was using some arguments that I couldn't quite generalize that well. And if we continue looking at this inductively, say we have 1, 2, now we have 2n minus, say, minus 4, minus 3, minus 2, minus 1, 2n, 2n plus 1. So now what we have is we have removed these two numbers. And out of these, we must remove n minus 2 of them. There's no way to apply the inductive hypothesis here. And that's where I got worried and stuck. Because now, if I'm thinking about, say, these numbers, can I apply the inductive hypothesis here? Well, I can if I don't remove either this number or this number. But the trouble is, if I remove either one of them, then I have to, if I remove both of them, I'm doubly in a messy situation. Then I have numbers 1, 2, 2n minus 8, 2n minus 7. I think I'm here, then I have to remove n minus 4 numbers, right? Yeah. I need to look at this set and I need to pray that none of these numbers, 2n minus 6, minus 5, minus 4, and minus 3, I have to pray that none of these numbers are removed, and then only then can I apply the inductive hypothesis. However, this is messy, so I tried something else. I tried, okay, if 2 is not removed, then let's say what if the k is the smallest one that is removed? Say the numbers that are removed are b1 less than b2 less than, say, bn minus, say, bn. Now k is the smallest one. What can I say about all these other numbers? What can I say about, say, 2k is removed, 3k, all the way till when is it removed? Like, am I looking at some like sets of remainders? Like, what is the sum then? How am I going to deal with this? Like, it was messy, and I had this idea, and I saw, okay, like the numbers that are removed are k plus 2k plus all the way till 2n minus 1 over k, the floor of that, times k, and plus 1 for the inductive step. And then, okay, but what about all the other numbers? What if I have a number that's congruent to 1, 2, till k minus 1 modulo k? What do I do with this? How do I get enough numbers? How do I connect this to n numbers? Like, it shouldn't work, but maybe it does work or does not work. It just did not. This idea seemed way too messy for me to do anything with it. And I mean, if you want to try something out, if you have any ideas, please let me know. I just could not take this further, and I found this induction so messy that I couldn't deal with this. And I remembered at the same time, which is important to do in your competitions, is to know like what level of competition it is, and what sort of ideas come up and what ideas don't come up. Say, if you're at the IMO, you know that calculus or linear algebra probably has a very low probability of coming up. You probably don't need it. Like, it's very rare. Like, for example, IMO 2020 problem number 2 is only one example I can see calculus being somewhat useful, and that's only if you know Jensen's as well. But you know, say at IMO 2016 problem number 5, that you're not going to be using calculus to solve the problem. And so here as well, you know, the JBMO is for students under the age of 15, so it can't use anything stronger than some induction. So then the idea that I needed to come up with was, maybe I need to look at, okay, all these numbers are removed. This is at least 3. I have at least n minus 1 numbers removed. Let me say n numbers. Let's look at it till 2n plus 1. I have these numbers removed. What can I do with that? And here is the part where I got stuck. And I'm going to teach you, and there's a very valuable lesson to be learned here. Maybe the most difficult thing to do when you're trying to solve problems is to, when you reach a dead end with one idea, or what seems to be somewhat of a more difficult, complex end that you're not sure if you can deal with or not, like this. I don't know if I can finish it with this or not, if I can get good estimates. Also with this thing, I don't know if I can get good estimates or not. Maybe looking at like the first couple of smallest numbers. Like, can that give me good enough estimates on both k and can I get n numbers removed? Like, is that good enough? And potentially the hardest thing to do that you really, I don't know, develop an intuition for, that's the best thing I can say, is to know when to go from exploring one branch of your solution finding tree, and go back to the beginning and try a different idea. And this is what we're going to be doing here. I would invite you, if you've tried ideas like this, I invite you to take a pause for the next 10, 30 minutes and figure out if you can get another idea to sort of connect this, to try to estimate what this sum, like b1 plus b2 plus bn, say bn minus 1 will work for 1 through 2n minus 1. What this sum is greater than or equal to, because like it needs to, we're looking for its minimum. So what is it greater than or equal? Take 20 and 30 minutes and try to figure it out. And here's the next big idea. Say these are all the numbers that are removed. And now what do we know about them? Well, say for b1, we know that b1 is removed. This is less than 2 times b1, which is also removed, and it's less than b1 plus b2, which is also, it's either removed or it's greater than or equal to 2n. And we know that these are all the possible sums that we could be getting, b1 plus bk. And now for b2, we could be getting b2 plus b1 with b2, this is less than this. Like, all of these numbers are either removed or out of range. b2 plus bk minus k, then we have b3 is removed, b3 plus b1 is removed, b3 plus b2 is removed, b3 plus b3 is removed, all the way till b3 plus bk. I mean, it's either removed or greater than or equal to 2n. And now the question is, when you write all of these up, when you write till bk plus b1, bk plus b2, all the way till 2bk. How can you estimate the sum b1 plus b2 all the way till bk? How can you make it greater than or equal to something? Like, what we need it to be greater than or equal to is what? 2 plus 4 plus all the way till 2 times n minus 1. That is, we need this to be greater than or equal to n minus 1 times n. And now that you see this as the important part of the problem, how can you estimate this? I invite you to take a look at this and think about this. Assume, say, b1 is greater than or equal to 3. And now try to estimate this sum right here. Take 10 to 30 minutes. So now that you've paused, let me tell you, I actually could not come up with this. I needed to find a solution. There was not a solution on the forums, and I found a solution on a Romanian site where this test was from. So what's happening here? So 1 is greater than or equal to 3. This is greater than or equal to 6. And then this, because it's greater than this, greater than 7, 8. And this is k plus 5. And then we have this. So this is, okay, 7, 8, 9. And now this is again, this plus 4, k plus 6. Maybe there's a way to estimate using this. But actually not even looking, let's say we don't start from 3. Let's make it even dumber. Let's make it first like the dumbest one. 1, 2, 3, 4 till k plus 1. And then we have 2, 3, 4 all the way till k plus 2. Then we have 3, 4, 5, 6 all the way till k plus 3. And now what we can do to estimate this nicely is to say b1 plus bk is greater than or equal to what? K plus 1. And so is b2 plus bk minus 1. greater than or equal to k plus 1. And so is all the way till bk plus b1. And when we sum them all up, what we get is that, say call this s, we get 2 times s is greater than or equal to k plus 1 times k. And because k is greater than or equal to n minus 1, we get that s, 2 times s actually is greater than or equal to n minus 1 times n. So now this isn't the estimate we like, this is actually half of our estimate. Though in competitions, it's important to even write down this if you find it. There might be partial points. And now let's go back to our list. We're not really using it fully. We know that really each of these numbers, this number, this one, and this one is either B2, B3, all the way till BK. This one is also one of those numbers, but it's greater than this one. So is B1 plus B3. And so we know that 2B1 is greater than or equal to B2. And we know that then B1 plus B2 is greater than or equal to B3, because this is greater than this. And then we know B1 plus BK minus 1, all the way up till this, is greater than or equal to BK, which means B1 plus BK is greater than or equal to 2n. It's not 2n minus 1, otherwise it would still be a bigger number. And now here I invite you to take 5 minutes and see if you can use this sort of idea to generalize it and come to a solution. And here's the next sort of thing. If you look at B2, so B2 is a member of the set, it's greater than B1. What about 2 times B2? Well, it's at least B3. What about B2 plus B3? Well, this one is at least going to be B4. And then what about B2 plus B4? Well, it's at least B5. Why? Because it's greater than this. It can't be B4. If this can't be anything less than that, it's at least B5. But there's something better that we're missing. We're missing that B2 plus B1 is less than this. So this can't be equal to B3 actually, because if 2B2 was equal to B3, and we had B1 less than B2 less than B3, then B2 plus B1 is greater than B2 and less than B3, but it's also a member of the set. So in fact, we have a better estimate. We have B2 plus B1 is greater than or equal to B3, and that forces 2 times B2 to be greater than or equal to B4, because it's a member of the numbers that are removed, or it's greater than that, or it's greater than 2n plus 1. Actually, it's greater than 2n, greater than or equal to 2n. And then we have B2 plus B3 is greater than or equal to B5. And so on and so forth. We have B2 plus BK minus 2 is greater than or equal to BK. And then B2 plus BK minus 1. It can't be in the set, so it's at least 2 times n. And if you think about our solution 2, 4, 6, all the way till 2n minus 2, this ends up being perfect, like k is equal to n minus 1, and then this equality holds. And all of these equalities actually end up being true. So now let's continue with this. And I mean, now you can maybe see if we can show that bi plus bk minus I is greater than or equal to 2n. If we can show this, then we will have, basically here, this was greater than or equal to k plus 1, which is greater than or equal to n. That's the estimate we use. If we have 2 times the estimate, we have 2 times the sum on the right-hand side, and we have s greater than or equal to what it needs to be. And now here, I invite you to take 5 to 15 minutes and see if you can write up a solution and connect all these ideas together. Here's the solution now. So we say, let the removed numbers be b1 through bk, where b1 is less than b2 is all less than bk, with k greater than or equal to n minus 1. And then for each I between 1 and k, we have bi is less than bi plus b1, less than bi plus b2, all the way till bi plus bk minus I. And we also add here bi plus bk plus 1 minus I. And now, if bi plus bk plus 1 minus I was less than or equal to 2n minus 1, then we would have a problem. And the problem would be then that bi plus b1 all the way till bi plus bk plus 1 minus I, all the numbers here would be, every single one of them would be an element of, this would actually have to be a subset of bi plus 1, bi plus 2, all the way till bk. However, because this set has how many elements? 1 through k plus 1 minus I, and this one has 1 through k minus I. However, because this set has less elements than this one, this means this is a contradiction. This would be impossible. So bi plus bk plus 1 minus I is greater than or equal to n for every I between 1 and k. And now we just finish this off with an estimate. Then the sum bi for I1 through k is equal to half of the sum bi plus bk plus 1 minus I for I1 through k. And then this is greater than or equal to a half times 2n times k. And now this is greater than or equal to, because k is greater than or equal to n minus 1, this is greater than or equal to n times n minus 1, which implies that the sum of a minus removed numbers, for I a removed number, is going to be equal to the sum of all I from 1 to 2n minus 1 minus the sum of I that's a removed number. And we know that the removed numbers, their sum by this is greater than or equal to n times n minus 1. So the minus their sum is less than or equal to 2n minus 1 times 2n over 2, 2n over 2, the 2's cancel out, minus n times n minus 1, which is equal to n squared. And we know that we can reach this n squared when? Well, when this thing is true for every I. But this thing is true for every I when all of these numbers are in fact equal. So with equality, if and only if bi plus bk minus I, we can just like use this maybe as an estimate, is equal to bk. Actually, let me be more specific. bi plus bj is equal to bi plus j for all I and for all j, such that j is less than or equal to what? Well, it must be less than or equal to k minus I and greater than or equal to 1. But if we just set I equals 1, that implies this quite quickly. That implies b1 plus b1 is equal to b2, b1 plus b2 is equal to b3, b1 plus bt is bt plus 1, and all of these imply that b1 times t is equal to bt, just quickly, inductively. And this thing right here, this implies, because we know that bi plus bk plus 1 minus I is 2n, and we know that bi plus bk plus 1 minus I is equal to 2n, i.e. I times b1 plus k plus 1 minus I times b1 is equal to 2n. And we know that this is k plus 1 b1 is equal to 2n. And now we have one of two choices. Actually, do we? We have k plus 1 is greater than or equal to n. And this implies b1 is less than or equal to 2. Can we solve this now? Well, if b1 is equal to 2, then we get our solution 2 for all the way till 2n minus 2. And if b1 is equal to 1, then we don't get a solution. We get k plus 1 will have to be equal to 2n, i.e. all the numbers will be removed and we'll have a much bigger sum. And this actually solves our problem. This shows that this is our only sort of set of numbers which works. And as always, thanks for problem solving.